Coming in hot.
Cool. So yeah, for anyone that hasn't attended before, it's going to be a nice succinct format today. You'll be able to join the Slido. We'll put the link in the chat.
All be ready for you guys, yeah, to, the format as before. We've got the card game. We've got some giveaways. Great talk from Jesus coming up, as you all know. So really glad to have you back so soon. And for some new attendees as well. You may see a little Gopher up there.
Big Gordon the Gopher. Yeah, really cool talk today. Golang. Last chat of the year before we wrap up for Christmas. So yeah, great to see you all involved. We'll share our screen so you can see the code here. Scan the QR code or hashtag dissecting for the talk today. Dissecting channels, slices and maps in Go with Jesus. Really looking forward to that. It's 1 minute to 12 now, so we'll just let a few more people come in, get set up on Slido. As always, we'll have the famous playing cards up for grabs. They have been shuffled and dealt out as normal. This time we're just going to draw them live, hold the card up to the camera, make it a bit more straightforward. So as always, like I said, have been shuffled and are completely random. So don't hold it against us if there's any surprises in there.
As always, wouldn't be a GoNaviro meetup without a few surprises. So
a few curveballs, go for playing cards up for grabs will be sent out. A few other prize giveaways as well. The format today, card game. Then we're going to do a half-hour tech talk with Jesus. And we're going to do a couple of quiz questions to test your knowledge at the end with some prizes there. And if we've got time, we'll run through one or two, the Q&A as well. So you can submit those in the Slido app. Also, again, we're putting together a schedule for next year. So any topics you want to hear about, just make sure you bang them into Slido and we'll take that on board and get something lined up for 2022 as well.
Yeah, absolutely. We've got some really good stuff planned already for the new year. We do have an upcoming GoNaviro special for early next year, but we are looking for recommendations from you guys on stuff you'd like our GopherCon and Gopher speakers to talk on. So don't hesitate to get in touch. Got a lot going on, but we're only as good as you guys in the community. So share with us what you like.
Cool.
All right. Numbers are creeping in here. Creeping right up.
Nice. So going to be rolling into the card game very shortly. I know there's a few repeat Golang E-Series attendees today. And so we'll give it a couple of minutes. There's a few people looking forward to this. So let a few more people roll in and then we'll kick things off and roll straight into the talk. So
you all know how Slido works, I think, by now. But for those who don't, if you've scanned that there's a QR code that you guys can see down there. If you want to scan that so that you're all involved in the Q&A, you can participate in a lot of the polls that we hold in terms of questions and everything else. You need to scan the code. I think the QR's down there. So just make sure you're involved or you won't be able to participate and win in some of those games. So good stuff. We're getting some numbers coming in. So I think we'll give it another
minute. We're just waiting for the main man himself. We've had a chat with him this morning, Jesus. So he'll be jumping on as a panelist very shortly.
Screen share. Right, there you go. I think the QR code should now be visible. We'll get that full screen. Can you guys all see that all right? QR code in the bottom corner there. Make sure you get it scanned up. There we are. Right, perfect. We're live.
Cool. All right. Kate, if you can bang over the link to Jesus so you can jump on. And yeah, then we'll get started. So just ping him over the link and we'll get going. All right. Awesome.
Right. How many have we got in Slido? They all signed up?
How are we looking on slide? Okay, we ready to roll with this?
16. Yeah.
Good, brilliant.
All right, perfect. So
go.
let's get into the cards game. You can join the quiz here. Big Domas Tamasukas, a previous winner, nonetheless, grabbed himself a Gopher t-shirt. So yeah, don't be shy, guys. Get involved. All good fun. It's a higher, lower, or the same. The Price is Right style, just with the Gopher playing cards. Again, these are up for grabs for the winner. So
yeah, we've got a lot of cards to give away, a lot of merchandise, a lot of GoLang stuff sat in our hold. So we're looking to get this out for Christmas. A few stockings under the tree for you Gopher guys. So yeah, get involved. We're eager to send it out.
All right, nice one. So
right,
let's go then. As I said, we're going to be drawing these live this time. Got the first GoNaviro playing card here, higher, lower, or the same. So it's a 7 of spades, little space, Gopher to boot.
Nice and easy.
5 seconds, get your answers in, guys.
Nice and easy.
Higher, lower, or the same. It's a 4 of hearts, so it's lower. 40% of you got that one right. Fantastic.
Lovely.
Rolling on to the next one, higher or lower or the same. It's a 4 of hearts.
So higher or lower than a 4.
Higher or lower or the same, 4 of hearts. Okay, let's roll.
We've got 7 seconds.
5, 4, 3. Boom. There it is. Of course it is.
There we go.
So little Gopher frying up a steak on the barbie. 21% went lower. Well done, guys. It's a 3 of spades. The same again, higher or lower, or the same. 13 seconds. Joe, you can draw the last couple out the hat here.
I'll go for this one. Higher or lower than a 3, guys. You already know.
5 seconds.
Naviro's special.
Your answers in, guys.
2, 1, and the slow roll is... We got a 9. Go on, 86% of you.
Strong.
Well done. I'd like to see a little dragon Gopher there for you as well. For those who haven't seen a dragon Gopher, he is there.
Nice work. Right, we've got the leaderboard here. So at the moment, Sergey is leading the charge. Also, fastest finger as well, guys. We've got Kate coming in a close second, also with 2 out of 3.
Well
Plenty
done,
of you
Kate.
here.
Lovely.
So before we get into this last one, just so you know, it is timed as well. So the sooner you can get your answer in there, more chance you've got of winning. A few people tied here. So playing for the cards. Let's roll into the final card.
3, 2, 1. So remember, it's higher or lower than a 9.
That's the same one,
What have we
Broomy.
got higher or lower than a 9. That's what we're saying. Remember. Go ball specials, eh? Right, 3, 2, 1.
All right, let's go. Roll them out.
Right, where are we? 4 ball lower. There it is.
Very
of course
nice.
it is. 65% of you getting it right.
65%.
There he is. Little upside downer. Brilliant, Mohi.
Oh, snatched it. We got joint winners again. So I think the last 3 times we've had joint winners. Jonathan, congratulations, Jonathan. I know he's attended a few of these too. So we'll get some Gopher playing cards out to you and to Mohit as well.
Really
well done. Unfortunate Sergey fell at the last hurdle. But yeah, next year we'll be rolling on again. So yeah, we won't delay any further. We'll start moving on with the talk now. So congratulations, guys, for taking part there.
Really well done. We'll be getting some of those out hopefully over the Christmas period. So you'll have something to open from the GoNaviro guys, a few decks of cards and everything else. So we are just locating the main man, Jesus, so we can get him started for you guys. And without any further ado, get the real content in. And don't forget, we have uploaded our first 2 videos. That was Preslav and Andre. They're available on the website, full hour long e-learning tools for you and anyone who might be interested in GoLang related content. It's available on the website. The others are coming. We are getting those edited. So stay tuned on GoNaviro for our full content bank available soon. So,
all timestamps for the important bits.
Just a few technical things here.
All right. So we've got Jesus. We're going to promote to panelist.
Right.
Seems like the right thing to do.
Jesus is joining. He is available, guys. He's
cool.
He's ready. We'll see you soon.
We'll switch over. We'll make Jesus the host now, so he can share his video and crack on with the talk.
See you soon, guys.
30 minutes, guys. Hope you enjoy it, and yeah, we'll catch you after.
Hi, everybody. I'm going to share my screen and start my presentation. Hello, I'm Jesus Espino. I'm software engineer at Mattermost, and I'm going to talk about dissecting channels, slices, and maps in Go. Well, for this talk, we are going to need some materials for dissecting our subjects. So we are going to need a scalpel, a microscope, and the subject itself. For slices, we are going to use unsafe as our scalpel. The scalpel is just a function that is going to get the data in memory that is pointing the slice and store that data, that binary data that is in memory, in a structure that we are going to analyze later. We are going to use a slice of integers for simplicity. We could use any other kind of slice, but for simplicity, I'm using integers. The microscope is another function that gets that structure and exposes that data in a simple way in the standard output. In this case, I show some memory address, some fields of that structure, and the data that is stored in the slice. The subject is, in this case, is a spline. We are going to see that that is actually an array of data plus one or more slices. It depends on how we use that. Well, inside the subject, what is actually a slice whenever you have that in memory in Go? A slice is just a pointer to an array. That is, an array is a sequence of bytes in memory, a continuous sequence of memory in the runtime, a length, and a capacity fields. That is all that is a slice in Go. Let's see an example of that. If I instantiated a slice of integers, in this case, I can use my scalpel to get that information from the memory and store that information in my structure, the structure that I defined before, and see that through the microscope and see what it means. In an empty slice, what I'm going to see is a pointer to an array that is not important because it's not, actually, I don't think it's a valid pointer. It's just random data there. A slice length, in this case, is 0 because we don't have any elements. A slice capacity, that is 0 because we don't have nothing to store, so we don't need to get any capacity to store nothing. And the stored data, that is just an empty list of things, that there's nothing stored yet. Let's get it more interesting. Let's add one item. If I add one item here, I'm going to have, now I have a memory address that is pointing to a chunk of memory that is going to store the content of the slice. In this case, it's going to store the binary value of 1. That is the content of that position in memory. The length is going to be 1 because it's the length of the array, of the size. And the capacity is going to be 1 in this case. That means that the memory, that address that we have there is pointing to a chunk of memory that only have a space for 1 integer. And the data stored in the slice is the integer 1. If I add more data, what is going to happen is, because I'm trying to add data and the array is not big enough, eventually that array is going to grow. Whenever I need more space, I need a bigger array to store the data, Go is going to reserve another memory chunk to store that that information. It's going to whenever the underneath array of the slice is not big enough, it's going to reserve another chunk of memory, a bigger chunk of memory, and copy over all the data from the previous array and add the new information in the new array and free the old array if it's not longer referenced. In this case, I added four more elements. So the array in memory, it has changed. You can see here that the address is different. And the slice length with 5, because we had before one element, I added 4 more. So I have 5 elements, but the capacity is 8, because the new array, whenever we need more space, we are not creating a new array with the space, strictly space that we need. We grow that array. We create a new array that have some spare space to add subsequent insertions. So in this case, what we have there is the slice capacity is 8 because the underneath array is 8, have a space for 8 integers in this case. And the length of the slice is 5 because that are the real elements that are referenced in this slice. We can create sub-slices. We can create a slice based on other slice. For example, here I'm creating a slice that say, hey, this slice is a sub-slice of the previous one, but it's starting in the position 1 and ending in the position 4. That is interesting because if I analyze the sub-slice, I can see that the array memory address is exactly 8, well, it's increased by 8. That means have 8 more bytes, is pointing to 8 bytes after in the memory. That is exactly the size of integer 64, that is the default integer in my machine. So that means that it's pointing to the same array, but in a different position of the array. So in this case, we are pointing to the same memory in the runtime, but we are changing the slice length to 3 and the slice capacity to 7. Why 7? Because it's the same array and the previous array was 8. But because we are moving our pointer a bit forward, it's no longer 8, the capacity, because we are not able to use the previous capacity. We are only able to use the capacity that is from your position to the end. So we have capacity for 7 more elements and the slice length is 3. And here's where the thing gets more interesting. We can modify the sub-slice, and if I modify the sub-slice position 0, for example, what I get is I'm modifying the sub-slice and the original slice at the same time, because both are pointing to the same memory. So because they are pointing to the same memory, we are modifying both. It's even more weird because this sounds like more or less obvious. Okay, you are getting a sub-slice here, I'm modifying it, and you are getting here, for example, modify the second value in the original slice and the first value in the sub-slice because, well, it makes sense, right? But what happens if I use append instead of assignation? If I append to the slice value 6, I get that here in the right position. So now the slice is 0, 3, 4, 6. But the interesting thing is that is affecting also the original slice. So if I'm appending this to this slice, to this sub-slice, I'm affecting the sub-slice and the original slice. And another interesting thing, if I keep adding elements to the slice, eventually that slice grows. and the underneath array gets discarded and get another bigger array and migrate all the data to that new bigger array. So if I modify the subslice after the growth, it's not affecting the original slice. So the behavior can change if the original slice has grown or not. So that is very interesting. So here's the code. If you at the end of the talk, there's some references. One of them is about all this code in a GitHub repo. So you can, this is the real code. You can take this code, execute this code, and you can see more or less the same behavior. You can change things there to play a bit with what is going on. And yeah, this is kind of interesting. Okay, maps. Well, the scalpel for maps is slightly different. We are just doing the same, getting the data from the memory address and storing that data in a structure. We are printing that information, the map information. The map is way more complicated than the slice. So printing the structure there is more complicated. The subject, in this case, I'm using along, is basically is a set of map metadata and some buckets to store the data that we are going to see now how it is translated to code. This is how it more or less looked like. We have a map structure that has the count, that is the number of elements that are stored in the map, the flags that I don't want to talk much about flags because it's not especially relevant for this talk. The B that represents the size, the number of buckets, but it's not exactly the number of buckets. It's kind of the number of times that the buckets has grown. And every time that the buckets grows is duplicating the size, the number of buckets, and is a number that have other meaning. But it's directly related to the number of buckets. Number of overflow is the number of overflow buckets. We are going to talk about overflow buckets later. The hash zero function, the hash zero is the seed of the hash. It is a random number that is generated every time you create a new map. And that seed is used to generate the hashes. So that is one of, that is one of the reasons why a map, you can't trust the order of a map because it depends on the hashing function, and the hashing function use this hash seed to get unpredictable ordering and unpredictable distribution of elements in the buckets. Buckets is a pointer to a chunk of memory that have a set of contiguous buckets. Every bucket is a fixed side structure that is going to have a very clear position in memory. So the list of buckets is a chunk of memory. All buckets is exactly the same. It's a pointer to another chunk of memory. And evacuate is the number of evacuate buckets that is used for the process of growing the number of buckets in maps. We are going to see that a bit more in detail later. Then we have all these, the buckets and all buckets pointers are pointing to the bucket structure, to an array of bucket structures. The bucket structures start with the top hash. The top hash is just a chunk of data that helps in lookups to know if the key belongs to the bucket or not, and is to speed up the process of finding the keys. I'm not going to enter into the details of the top hash, but is every time the keys inside a bucket changes, the top hash is going to change. Then we have an array of 8 keys and an array of 8 values that are always 8 and that are always a fixed size, because the type that you store in the map, the key or the value, have fixed size. Then you have an overflow pointer that can point to another bucket, and we are going to see why that is there later. Okay, let's create a map, a simple map with nothing in it. You are going to have map size 0, the flags. We are going to ignore some data there. The flag is going to be 0. The B is going to be 0 because the map hasn't grown ever yet. The number of overflow buckets is an approximation, but it's 0 now. The hash sheet, that is a random number that is generated when you create the map. The map bucket is the address of the initial bucket. In this case, when you create an empty map, this has one single bucket. The all buckets is nil because we haven't grown the map yet, and the number of evacuated buckets is 0 because we haven't grown the map yet. Okay, if we add one item to the map, in this case with key 1 and value 10, the map size is now 1. The B is equal to 0 because the number of buckets is not grown yet. And what has changed there is the bucket 0 is receiving the new data. It's receiving the key and receiving the value. It's updating the top hash, and the overflow pointer is still null because there's no overflow. If I add more data, what is going to happen eventually is the bucket is going to grow. The map is going to grow, and a map grow creating a new set of buckets, asking for a new block of memory to store more buckets. In this case, after adding 8 more elements, we have a map size of 9 with the B value equal to 1 because has grown 1 time. And there you see the buckets, and the buckets are kind of randomly distributing the data in both buckets. That is done through the hash function. The hash function is going to take any key and generate a hash, a number that every time for the same key is going to have always the same value, but that is done also with the hash sheet. The hash sheet is going to be used with the hash with the key to generate the hash, and then it's going to get the reminder of that hash between the number of buckets and all that stuff to just select what bucket one key go. What bucket is the bucket that a key ends up being inserted. So here we have 2 buckets. In each one of them have different values that are inserted. Everything looks good. You can see there that has grown, but the whole bucket is still nil. The number of evacuated buckets is 1. What happened is whenever a map grows, it doubles the memory of, it reserves a new block for buckets that is going to be the double of the existing one, and it's going to start migrating that data. If you have only 1 bucket, that process is going to generate the new bucket and it's going to migrate everything in one shot. So that is going to be automatically migrated everything in one shot. But if you have more buckets, that process is not going to be able to migrate everything in one shot. We'll be able to migrate everything in one shot, but this by design is thought to not migrate everything in one shot, to not allow the map to block the process to doing a huge amount of migration of data. So It creates a new set of blocks. It and migrates some data there, and in the subsequent insertions and deletions and modifications, is going to start migrating buckets from the old buckets to the new one, and then that is where the number of evacuated buckets gets important, because is what he is going to say you if you have migrated everything already, or you still are in the process of migrating. Whenever you migrate everything, the old buckets get removed, the old buckets pointer get removed, and the memory can be freed. Okay, so it's important to know that the hash function that is used to distribute the data in between different buckets is defined by Go, and you can't define that by yourself. You can't really define how this hash function works. The reasoning behind that is hash functions are really hard to get it right, so the Go team get that right for us, and we can just use the hash function. Well, you have, let's talk about overflows. Imagine that I added 4 more elements, and that 4 elements, because because bad luck get randomly assigned to the bucket 1. So the bucket 1 get full, but the amount of data in the whole map is not enough to trigger a resize of the buckets, but it's enough to fill one of the bucket and need more data to store, need more space to store in that bucket. In that case, what is created is what is called an overflow bucket. An overflow bucket is just another bucket that is storing it in another place in memory, and the bucket have a pointer at the end that is the overflow pointer. The overflow pointer points to another bucket that is going to store extra data. In a normal map, we can have multiple overflow buckets, but it's not super common, and it's cheaper than having to resize the bucket every time that this happens. Well, we can see here that in this case, the map of number of overflow buckets is 1, because we have 1 overflow bucket, and that's it. As I said, when we have big resizes, the new set of buckets gets reserved, the new values inserted are in the new buckets, the old buckets are still in use. We have to search in the old buckets and the new buckets on lookups for some time, and the data is getting migrated gradually in the subsequent operations. Here is the code for the maps. As I said before, I have a GitHub repo with all this code. And let's talk about channels. This is the scalpel for channels. Again, getting a channel that is in memory and getting that into a structure that I can analyze and can visualize. Here is the information that I extract from that in-memory structure. Here is our subject, that is a neuron. In this case, we have the channel inputs, the channel outputs, the channel internals, and the open and closed concept of the channel. If we open the channel, we can see that this is what we have inside. We have the Q count. The Q count is the counter of how much data is stored in the channel buffer. The data queue size is the amount of items that the queue is able to store. The element size is the size of each element in that queue. The buffer is a pointer to a chunk of memory that is storing that queue. Closed is just a value that says if the channel is open or closed. The element type is a pointer to the element type. In this case, can be integer, can be float, can be a string, can be whatever, but we can have, we have a pointer to that element type. SendX and ReceiveX are two pointers, two integers that are pointing to the position in the buffer that is the next position to insert or the next position to read. The receive queue and the send queue are two coroutines queues that are there to store what is, to store the coroutines that are waiting for receive data or waiting for send data to the channel. Let's see an example of that. If we create a channel with of integers 32 and with a size of 4 elements, of a size of 4, a buffer size of 4 elements, we open that with our scalpel. We see that with our microscope, and what we see there is we have a queue that have 0 elements in it, that have a size of 4 elements. The element size is 4 because it's a int32, so it's 4 bytes. And the queue elements, in this case, what that pointer to memory is pointing to that data that is 0, 0, 0, 0. It is not closed, so the value is 0. The element type address is a pointer to the int value, to the int type in memory. And well, the buffer address is that. The send index and the receive index is 0 because it's pointing to the first position in the buffer, and the receive queue and the send queue is empty for now. Let's see what happens if I insert one element in the channel. If I insert one element in the channel, it's going to increase the queue counter, so it's going to be 1, and it's going to insert here the element 5 that I'm inserting, and move the send X 1 position ahead, 1 position forward. So that is what is happening under the hood. What happens if I add more data? For example, I have a buffer of 4 elements, but I'm going to add, instead of 4, I'm going to add 5. I added 1 before. Now I'm adding 4, 3, 2, and 1. But when I added 4, I remember that send X was here, so I added 4 here, I added 3, I added 2, and I tried to add 5. I tried to add 1, sorry, but there's no more space in the queue. So what I do is take the coroutine, pause that coroutine, and send that to the wait queue for the channel. So that coroutine is stopped there until this channel decided have some space to store that data. If I read from the channel, what is going to happen is I have the receive X pointer here, and the receive X was pointing to the 5, so I return the 5 value and a true because the channel is open, and I move the receive X to here. And because now I have 1 space here, because I'm extracting some information, I'm going to wake up this coroutine that was here. I'm going to wake up that coroutine, and that coroutine is going to add the 1 element here in the position that was the send X position. So that is how it is going to work. Still, the number of elements is 4. I can get more data. In this case, I'm getting a 4 element that was the receive X was here, so I get the 4 element. I move the receive X to the next position. I can, and I decrease the number of elements in the queue. I can keep going and until there's no more data, and here there's no more data, and suddenly another coroutine gets in and try to read more data. What is going to happen is I'm going to stop that coroutine. I'm going to send that coroutine to the receive queue, and it's going to wait there until somebody inserts some data. If somebody inserts some data, it's going to go here and send the data to the, wake up the coroutine and send the data to the coroutine, and the coroutine is going to keep working. If I close the channel, I set this value closed and I send this 0 value and false. That means that the channel is closed. And this is all about channels. This is the code. If you want to reproduce this experiment, again, it's in my GitHub repo. These are the reference. All this information is more or less easy to get if you go to the Go code. In the Go source code, in the runtime directory, you have the slice, map, and chant files that explain that have all the information of how the slice, maps, and chants and channels work at runtime. Here is my code around this. All this code that I have shown is available there, and that's it. Thank you. So I'm going to change the.
Hey, Jesus, fantastic work, mate. Well done. That was awesome.
I'm going to. I don't know if I have to change something.
No, we can just reclaim the host here, and then we'll share our screen after that, so that you've got the questions for the next part. So. Perfect. Just bear with us 2 seconds and we'll just load all of this up. That was great, mate. So
yeah, no, really good presentation there, Jesus. The imagery, I mean, from what I could understand, it was really well documented and presented. Yeah, the feedback's been great so far as well. So thanks a lot.
Thank you.
Nice one. Cool. So yeah, what we'll do is we're back on host mode here. So if we share our screen and then we can just run through these 3 questions you put together, everyone can test their knowledge, and we'll also have a prize giveaway for that again as well. Whoever can get the most right answers, and obviously the time considerations are there as well. We'll shoot some Golang cards and some other prize giveaways over to the winners too. So, right, yeah, just sharing here. If we just pull up the main quiz, so we've got a few of you guys joining already.
Quick guys, getting the quiz.
Mohit's going for the double today, by the looks of it.
By the way, guys, you can still ask some questions as well. Remember, at the end of this, we will have some quick time to ask Jesus some questions from you guys. So if you have any questions from that presentation, put them in the Slido app. You can just say ask. I think it's in the Q&A part next to poll. You can ask any questions for Jesus, and if we have time, we'll get them across.
Yeah, awesome. All right, cool. So yeah, plenty of people jumping in here. Sergey was leading the charge in the cards games. Hopefully can get the gold this time.
Domas looking for redemption as well.
Just before we get into the questions, but really appreciate everyone coming on board today and taking part in this. As I said, we will be sharing the content on the website. We know this is really valuable stuff. Obviously, our business is dedicated solely to Golang hiring. The market is very exciting at the moment for relocation, remote opportunities with some cool companies, and any ways of skilling up in this game at the moment is certainly going to put you in strong favor. So really appreciate you taking the time today, Jesus, and sharing your knowledge, mate. It's much appreciated. So cool. All right, we'll run on to the questions, which we can let you guys crack on with.
Yeah, ready to go, guys. 16 of you, ready and waiting. Right.
What is true about slice and an array in Go? So you've got 4 options there, 10 seconds.
We have the same thing in Go. Slice contain arrays, arrays contain slices, or slices data is stored in arrays.
2 seconds to roll.
I know what I think. Oh,
nice. 58% you got that one right.
Well done, guys.
Is that kind of what you thought, Jesus? Do you think more people would get it? Less people?
Yeah, well, this was tricky because slice contain arrays is kind of something that you can think, but it's a clear division between that. But yeah, Kind of expected, yeah.
Nice.
Good to hear. Go on, team.
Cool.
Next question. Right.
Question number 2.
When a map grows, how is it done?
We add more memory to store the new data. We add more memory and migrate everything to the new memory. We add more memory and start migrating the data gradually, or we compact the data to make space for more. 5 seconds.
Well,
All righty. How you getting on, mate?
yeah, well, not too well at the moment.
And the answer is we add more memory and start migrating the data gradually. So again, 54%, just over half of you guys got that one right. Do you want to just explain that a little bit more, Jesus?
Yeah, it's exactly that. It was a tricky one too, because it's what you can expect there is as well adding more data or more space for the data. But in this case, is what happens is you reserve more data and start migrating, but not everything at the same time. It's just slightly, slowly migrating that data to not affect the overall performance of the application in a very specific point.
Nice, perfect.
Lovely.
Right, question number 3.
Next question.
Let's roll on. Can I define the map's key hash function?
Yes. Only for not bulletin strunks. Use define strunks. Only for bulletin objects, or no?
A, B, C, or D?
Apologies for any mispronunciation there, guys.
2 seconds, guys. All right. Can I define the map's key hash function?
Wow,
and the answer is
close. Oh,
no.
Half
No,
of
you can't.
Brilliant. Can't do it, and you knew it. Well done, guys. Right, we'll go to the final question here, shall we?
Yeah, roll on. What happens if a map bucket is full and I add something new there? The map grows, a new bucket is created to store extra items for that hash. The new item gets added to the next bucket, and out of memory panic gets raised. A few seconds, guys.
Nice and easy. Whoa, this will be interesting.
Oh, another 2 around 50%. Oh, there you go. New bucket is created to store extra items for that hash.
You should all know that, but we'll let you off.
There you go. 47% you got that one. So let's let's just elaborate a little bit on that, Jesus, if you can.
Yeah. The thing is, there's whenever the map needs more space for a specific bucket and there's no growing the whole map, it's just adding extra data, extra space at the in another point of the memory. It's adding extra space, creating a new bucket for that, and adding in the overflow pointer is what is called an overflow bucket. The overflow pointer of the current bucket is going to be assigned to that new memory address. So it's going to point to that overflow bucket, but it's not going to get added to any other bucket that is already exists or something like that. It's a completely new bucket that is created on purpose for that overflow.
Nice.
Brilliant.
Nobody went for the map grows anyway, so hopefully that was the fun answer. Nice one. All right, let's get to the results. See how you guys got. Thomas,
he did it.
Repeat winner. Nice work, mate. 4 out of 4.
Lovely.
And in 48 seconds, just Pip and DG, and Mohit is very close.
Jonathan
again
up there as always.
Same with Jonathan and Sergey. So yeah, well done, guys. Strong effort today. Thomas, I'll be in touch with you to organise the prize giveaway. We'll get some cards over to you and see what else we can put with that Gopher t-shirt that you got last time. And once again, thanks very much, Jesus. I think we have got a couple of quick questions here if we've got a couple of minutes.
Yeah, absolutely. I don't know if you guys can see in the Q&A on the Slido there, but we've got 2 questions. One from Ben Schumacher for you, Jesus, and it's, why is channel struct closed and unit 32 and not a ball?
Well, that is a question probably for some Go developer. I can guess. My guess there is probably about how to handle the memory in the structures in the channels itself. Because if you start using booleans there, probably is a lonely Boolean, and you are start making the struct less more compact, but less easy to handle in memory and all that stuff. I'm not 100% sure about that, but my guess will be that use a uint32 instead of using Boolean, or using other smaller type to get the data more keep the data easier to access and easier to be handled by the CPU. But as I said, I'm not a core developer. I don't know exactly what was the reasoning behind.
Yeah, it'd be interesting. Anyone knows the answer to that, ping us in, and we'll share that round on the group and on the website too.
We got another question actually come through from Ben. Why is slice.len and slice.cap an int and not an unint? Can they be negative?
Good question. I don't think so. I think they can be negative. I'm not 100% sure if the implementation is an int, but I think it's an int, but I'm not 100% sure about that. And yeah, I don't think can be negative, but it's the current implementation.
Yeah,
that's what it is. I don't know.
Yeah, fair enough. Ben's obviously coming in with some challenging questions, but yeah, look, this is what we want anyway, guys. Anyone knows or has some input on that, then ping that through. And we'll get through one more question.
Top up voted here from Cigar.
So why is a map an unordered collection in Go?
That is by design. That is a decision made by the Go team to not make it predictable. One, the hash function, they need to build, they want to build a really good hash function. And that hash function needs to have certain properties, like has to be randomly distributed, has to have certain features. And one of the features has to be unpredictable about what buckets are this function going to put the value in. And because of that, and how the buckets, how the data is, how the maps are iterated in Go, makes impossible to get it sorted by default. The reason for that this hash function having completely random assignation of the bucket is to avoid attacks like, okay, I know that the 72 and the 145 goes in the first bucket, for example, always. So I'm going to get all the data that is going to go in the first bucket, and I'm going to force your application to start using that, and I'm going to trigger a lot of overflow buckets, degrading your application, your performance, all that stuff. I can mess with your memory somehow, mess with your memory usage if I know which buckets are going to be used for certain keys. So that is one of the reasons that we have this hash sheet that is for forcing completely random maps. So you have 3 maps, for example, and that 3 maps have the same keys, and they don't have the same order, and they don't have the same buckets, and they don't have the same in-memory structure, because it's completely different and it's completely random for each map. That makes hard to exploit that weakness that can have a hash function.
Nice one, mate. Yeah, very comprehensive answer. We've got a few more pinged directly, but we'll wrap things up today, and we might send a couple of those over to you in email, mate, if you've got any time just to come back to us. I know it would be much appreciated. And once again, wanted to thank everyone taking part today. We've got another event kicking off the start of next year with a guy called Klaus Post, really accomplished Go engineer. He's talking some interesting stuff around data serialization. So we'll share more details on that with you guys. Hope you all have a great Christmas. And we'll watch out for the video. We'll keep everyone updated with next steps from there.
Yeah, absolutely, guys. As Joe said, Merry Christmas to you all. Have a great time. And don't hesitate to get us in anything you want for next year. We're always looking to add to the community. But Jesus, look, big thanks, man. Really appreciate it. It was a great talk. That presentation was first class, and we can't wait to get it edited and up on the website and out to the community. So big thanks to you, Jesus.
Thank you. And thank you, everybody, for coming.
Good man. All right. Guys. Take it easy, guys. Enjoy your day.
Bye-bye, guys. Bye.